Thank you, Jean Maria. It's really great to finally have this workshop come together and be so successful with so many participants. And I hope that we will, do many similar things like this in the future. So what I'd like to talk about today, basically the purpose of my talk is going to be to set the stage for what DeBrage is going to talk about. And so what I'm going to do, some of this information is things that most people have maybe heard of. A lot of it is new, but I'm going to try to really paint a picture to motivate what DeBrage is going to do. So I'm going to be talking about deficiencies of the Bergman projection. One thing that we've seen many times throughout this weekend has been, oh yeah, Bergman projection. Sometimes it has a limited range of LP mapping properties, but we're going to investigate that a little bit deeper and say, like, in what ways can LP boundedness fail, and we'll also look at this other question of, hey, even if the Bergman projection is bounded from LP to AP, sometimes it's not even surjective onto AP. There's some kind of a null space. There's a certain subspace of AP that gets mapped to zero. And so these are some serious deficiencies if you're trying to use the Bergman projection as a tool to study AP spaces. And so I'm going to focus this talk on two very concrete examples: the Hartogs triangle and an even simpler one on the punctured disc. And just to make these as concrete as so, if certainly if these deficiencies are arising here, then in more general settings, then they can also appear too. And then the third thing that I'm going to talk about after I've went through these deficiencies is we want to come up with a better operator to do what we're trying to do, which is to study this AP spaces with. And so we'll talk about the Sub-Bergman projection, which is something that maybe you've seen before. It was introduced by myself, DeBrage, and Jeff McNeil in 2019. And then this basis projection, which this I can say is the world debut of this thing. So, all right, let's move on. So, of course, this is the Hartogs triangle. I'm pretty sure everyone in the audience has seen this by now. And let's highlight two important facts. So the first one, everybody will know this, who's in this meeting. It's bounded from LP to AP if and only if P is in this range. Here's another fact that some people here may know, but it's less commonly known, that the Bergman projection it's bounded for this interval from 4/3 to 2, but it's not surjective onto AP for this range. And so in a sense, B, this operator, it's not even a projection onto this space, but I'm going to continue to abuse language and refer to this operator as the Bergman projection, even in the setting where it's not actually a projection. So let's take a closer look. What goes wrong if P lives outside of this interval? Well, so the first thing to notice is Z2 can't ever be zero. And so certain negative powers on Z2 can be allowed in a function, might be, it could be holomorphic. And then we're wondering, when are these monomials L2? And you can very easily draw a picture of the L2 monomials. So everything in the first quadrant is fine because those are nice bounded things. In the fourth quadrant here, there are a certain, a straightforward integral calculation will show you that these dots, which I've circled in cyan here, are L2 are L2 functions. Okay, and so it turns out that all of the imagine everything in the first quadrant being circled in blue too, and so these cyan dots end up giving you end up representing a basis for the Bergman projection. or the Bergman kernel. And so we can express this as this infinite sum over this set, where this set is the set of the cyan dots there. Now, in the case of the Hartogs triangle, this can be evaluated explicitly, and this formula here is what the Bergman kernel of the Hartogs triangle looks like. So we'll use both of these, shortly here. Now, let's think about failure of LP regularity. So I already showed you this L2 diagram. Let's get more precise with it. And so what we're looking at here is now, I not only have the L2 lines still, but now I've drawn in more lines which correspond to integrability. And I have more lines which correspond to integrability. So this is the L1 line, the L4 thirds line, L2 line, L4 line. Is there a question?
No, I think it was.
Okay, sure. So what we're looking at here is this line. These are L2 monomials, but they are L2 and they're in fact LP for all P up to, but not including the next line, which is 4. So these things are L4, and it turns out I have this infinity here. All the L4 monomials turn out to be automatically L infinity on the Hartogs triangle. And same thing here, we have an L1 monomial. It turns out this thing is LP for all P up to, but not including 4/3, and so on. So that's how you kind of read this diagram. And so what we're going to do is we're going to try to exploit one of these magenta monomials to demonstrate the failure of LP regularity. I mean, this is, something that I think Eunice and DeBrage did, and something Jeff and I did, 5 years ago. But I'd like to point this out. So suppose you take this nice bounded smooth function, Z2 bar, anti-holomorphic thing. Well, if you calculate the Bergman projection of that, then the orthogonality of the monomials ends up giving you quite easily that this Bergman projection is a constant over Z2, which corresponds to this dot here. And as I said, on the previous slide, this thing it's L2, but it's LP for all P up to, but not including 4. And so this gives you the failure of LP regularity for P greater than or equal to 4. Now you can of course use duality to sort of determine the lower half interval, but I'm going to illustrate this, for P less than 4/3 in a different way. When P is less than 4/3, this this boundedness of the Bergman projection fails even more drastically than it did for the upper interval here. So let's say that we take this function here, Z2, 1 over Z2 cubed, which corresponds to this dot here circled in red. Well, as I said, it's L1. In fact, it's LP for all P up to, but not including 4/3. So what happens if we try to take the Bergman projection of this thing? Well, so the Bergman projection is carried out by calculating this integral. So by taking that function, let's temporarily fix a Z and look at this and ask ourselves, like, is this even L1? Well, we can plug this in and do a little bit of manipulation, get to this stage, and then do a few quite simple estimates and end up estimating it by this from below. And of course, this integral here blows up. And so the Bergman projection of this function on the Hartogs triangle isn't even well defined. And so like it's more. So let me reformulate it this way. Say we let chi n be a sequence of radial cutoff functions in radial in the Z2 variable, excising a circle of radius 1 over n around the Z2 equals 0. Okay, so then we're going to have that, this limit in the LP norm will tend to 0 as n goes to infinity. And by orthogonality, since we're cutting out the part where this is blowing up, by orthogonality, this is Bergman projection of this thing's always going to be 0, but you know, in the limiting case, we can't even really talk about the Bergman projection of this function. And so this it's not even a closable operator for p less than 4/3. So there's some, you know, serious deficiencies that we're looking at. Another thing, you know, to point out is this failure to reproduce AP, as I mentioned. So we know that it's bounded in this range, but you know, suppose that we have, so we'll define SPH to be the set of multi-indices where the monomial E sub alpha is pth power integrable. A function f in AP can always be written as a Laurent series, you know, where alpha ranges over this set. Okay. Well, if we look at the picture here, so we've got the Bergman projection, of course, is built up from these cyan colored dots. Well, an AP function for p in this range might have, you know, non-zero coefficients corresponding to these orange dots here. And so when you calculate the Bergman projection of such a function, if any of these orange dots have a non-zero coefficient, then you're going to get that the Bergman projection, which is equal to this, is not equal to your original function that you started with. Okay, so you really, you know, these are quite simple things going on that you can illustrate easily with a picture like this, but nothing like this happens in the smooth setting. And so I think it's quite important to kind of put your finger on the ways that this goes wrong as we try to now, you know, fix and repair the situation. Now, of course, this failure to reproduce AP for p less than 2, this is something that's apparent. Not even you don't even have to look at the Hartogs triangle; just look at the punctured disk. So, you know, this monomial 1 over z. This is a nice LP function on the punctured disk for p less than 2, but of course it failed. You know, 2 is the threshold where it's not L2. So, you know, what this says is that the Bergman kernel, it can't see any of these punctures. Okay, but you know, so the Bergman projection on the disk, which is built up from the L2, you know, looking at L2 stuff, so it misses all the punctures. The Bergman projection on the disk is the same thing as on the punctured disk, and since it's only built up of these L2 monomials, it will annihilate any term in a, you know, function in AP if p is less than 2, corresponding to this orange dot here, getting this same thing where the Bergman projection is not equal to the original function. So, you know, so this is kind of what's going on here, and so let's summarize this. So to recap, B might not be bounded as an operator from LP to AP for certain P not equal to 2. It might not even be a closable operator on LP for certain P less than 2. And even if it is bounded from LP to AP, it might not even act as the identity map on AP. So we have to face the facts that you know, kind of an inconvenient truth here, since I'm talking about this in a workshop dedicated to the Bergman projection, but the Bergman projection is not a good choice of an operator if we're going to study AP spaces in these types of settings. So we need to, you know, we need to come up with something that these bullet points, you know, don't happen here. Okay, so substitute operators. So I'm posing as a problem. In situations where B is a deficient operator, can we build a better one? So in other words, suppose for a fixed P between 1 and infinity, we want a substitute operator that's going to be bounded from LP to AP, and if we're restricted to AP, then we'll get the identity map. So one thing to say is we you know, might expect our operators to actually vary as we change our p value here. I mean, with the Bergman projection, you're taking the Bergman kernel, which is sort of built up from L2 stuff and then seeing how it spreads into other spaces. And so the first approach I'm going to talk about is quite closely connected to the original Bergman projection, but summed over a smaller set. Okay, so fix some P probably greater than 2, because at 2, it's just the Bergman picture, okay? And we'll return to this lattice point picture. So what about the Bergman projection? What about the Bergman kernel obstructs LP boundedness? Well, so we've seen a few slides ago that if P is greater than or equal to 4, the obstruction LP boundedness comes from these magenta monomials, which are on the L2 line, but then they're not L4. So what if we toss them out and just define this thing called this P Bergman subkernel, where we're adding up the same things, but now over a smaller set. We're only adding up over the cyan monomials. The magenta ones we're forgetting about, okay? And so on the Hartogs triangle, we have this theorem that, Debraj, myself, and Jeff proved a couple of years ago in a more general setting, but, just stated here. So if we fix P greater than or equal to 2, this P sub Bergman projection, denoted by this, is a bounded operator from LP to AP, and it's surjective onto AP, okay? So yeah, I said we introduced this a couple of years ago. The analogous theorem holds on a wider class of domains. Debraj is going to talk about this. On the Hartogs triangle, it's important to notice the form of this thing, it stabilizes when P is greater than 4, since, as I mentioned, the L4 monomials are also L infinity. However, in more complicated domains, we'll have more representative kernels as we vary what P is going to look like. So really in this case, we've only got 2 different things: the full Bergman kernel, which is gonna work from 2 all the way up to 4, and then at 4 there's sort of this threshold where now we have this different operator, and that has better mapping properties. But okay, so this this is a step in the right direction, but this is not going to help us do anything to address the other problem, the failure of reproduction, which happens for P less than 2, because we've taken away monomials. We need to think about how can we somehow incorporate these other monomials into the picture. And so if we're going to do that, well, we have to move away from L2 for the following reason. So it's a step in the right direction, but these things, they rely on the L2 norm of this monomial in the denominator. And so we can never, we'll never be able to introduce new monomials into the picture if we continue to talk about this, the L2 norm there. And so, yeah, we need to do something to incorporate these orange monomials into the picture. So this monomial basis kernel that we are, talking about, and Debraj is going to, further elaborate on. I'm just, scratching the surface here. So let P be a fixed number between 1 and infinity, omega be a Reinhardt domain, and lambda be a positive weight function, which is radial in each one of the ZJ variables. Okay, and so we'll define this thing similar to before, SP omega lambda, to be the set of multi-indices such that this monomial here is LP with respect to this weight. And then we'll also define R of Z to just be this ntupole of absolute value of ZJ in the jth coordinate. So define the monomial basis kernel to be this object here. Okay. So I can, write this down. Right now we don't even know that this is a useful thing to even consider. Does this even converge on omega cross omega? It turns out it does. Debraj is going to show that. Holomorphic, by looking at this, holomorphic in Z, so it's definitely going to be, if we can integrate against this thing, it's going to be giving us holomorphic functions, but it's not anti-holomorphic in W, except in the case when P is 2, when this of course coincides with the Bergman projection. And but you know, the really important thing is that this incorporates all the monomials E alpha from the space that we care about into the formula. Now, you might ask, like, okay, why am I talking about this weight? Well, first of all, I mean, I think it's interesting to investigate the you know, weighted problems in their own right, but specifically, what we're going to do is, you know, I'm gonna end with proving a result on the punctured disk with respect to some weights, and then we're going to use that to cover things in higher dimensions. Okay, so okay, so you might be like, okay, where the hell is this formula coming from? There's a, you know, very good motivation behind it. So this function, let's define G sub alpha of W to be this thing, which of course was just, you know, was just this piece here. So this Kp lambda of ZW, it can be expressed this way. Well, okay, so suppose that we look at the linear functional that takes an AP function, F, and sends it to the coefficient of the monomial E alpha in its Laurent expansion. So it's you know, quite straightforward to show this is a bounded linear functional, calculate what its norm is. And so it turns out there's going to be a unique Hahn-Banach extension of this functional, which we'll denote by A alpha tilde. And this Hahn-Banach extension of the functional, when we extend to the full LP, is given by integrating against this guy here. Okay. And of course, when P is 2, this is just this, which is it's the moment integral that's used in the classical Bergman projection here. So this is we're building this thing up from these Hahn-Banach extensions of coefficient functionals in the AP space as opposed to the A2 space. Okay. So how am I doing on time? Okay, yeah, good. So the monomial basis kernel on the punctured disk. So let's fix P, you know, anywhere in this interval from 1 to infinity, and we'll let lambda of W be absolute W to the gamma power, where gamma is any real number. Okay. So the monomial basis kernel for this space ends up taking this form, where T is now this guy, and L is this integer here, depending on both the weight and the P. All right, well, you know, you might think, okay, that's kind of, you know, ugly looking, you know, like for instance, this thing is often going to be a negative integer. Okay, and so you have you're now sort of building this pole, or yeah, this pole at the origin into this thing, as opposed to the you know, the classical Bergman projection. So I think another thing to point out too is, you know, you might be a little bit troubled at first by like these floor functions, but really, like, if you've ever worked with this kind of stuff and you know about, like, you know, varying P or varying your weight, there will be certain thresholds where all of a sudden you go past a certain point and then there's a new monomial that's allowed into your expansion of your functions. And so you shouldn't be troubled by this. And it turns out, even if it might not seem like it at first glance, but this formula in fact does vary continuously with P. Okay, and so that's you know, a stark contrast to the P Sub-Bergman kernels that I just talked about a minute ago, where it's the same thing until you get to a threshold, and then there's a jump to a different kind of kernel. Okay, so very easy to check that this thing recovers classical Bergman kernel when P is 2 and the weight is 0. But the most, you know, as I said, the most important thing is that for P less than 2, this kernel is now seeing the puncture in the unit disk, and the classical Bergman kernel can't do that. Okay, so so now mapping regularity of this. monomial basis projection. So we define, I guess I didn't define the projection, but of course it's the obvious thing. You know, take a function, integrate it against this kernel with respect to, you know, with respect to this weight here over the punctured disk. Well, you know, a really kind of cool application of this two auxiliary function Schur's test, because this kernel is very much not conjugate symmetric anymore. So you need two auxiliary functions, but you know, you can work this out that this for any p fixed between 1 and infinity and any weight of this form, this monomial basis projection on this space is a bounded operator. And you know, so we have some kind of an estimate like this. And by the construction of this thing, this is guaranteed to be, you know, once we know that it's a bounded operator here. In fact, it's absolutely bounded also. Since I said we're using Schur's lemma to establish this, we immediately obtain that it's going to be surjective onto the space just by, remember, we built this kernel up by making sure to include all of the monomials in that space. And so this let us get past this deficiency where you know, it's not reproducing the space that we're projecting onto. And so so perfect. I've only got 1 minute over. So yeah, let me just finish by saying, so yeah, to recap what we did here on the punctured disk, we built an operator that has better mapping regularity than the Bergman projection. And in part 2, Debraj is going to really kind of develop the general theory of this. In particular, he'll use the fact that this is bounded on this space, as I just said, to prove an analogous result on a much larger class of domains in CN. And this class of domains, in fact, contains the Hartogs triangle. And so that's that. So thank you.